Assalamu alaikum. Dear viewers, I am Dr. Noshin Afshan and you are watching the lecture of Inorganic Chemistry with the special topic of discussion being valence shell electron pair repulsion theory. According to VSEPR theory, the different molecules have been categorized under different systems that are AB2 system, AB3 system, AB4, AB5 and AB6 system. And these systems have been subcategorized into different systems. For example, AB3 has been categorized into AB2E system and AB4 into AB3E and AB2E2 system. And all these systems and their categories or subcategories have been designed depending on the number of bond pairs and number of lone pairs. So their detail is explained here. According to AB2 system, the molecules have been designed like they contain two number of bond pairs and there would be no lone pair of electrons. In this way, these two bond pairs would be arranged around the central atom, that is A here, at the maximum distance from one and each other and at the minimum repulsion. So the maximum distance comes to be at the 180 degree. Hence, if we draw their molecular shape or the bond pairs at 180 degree in this way, then the geometry comes to be linear. And examples under this AB2 system come out to be beryllium hydride, beryllium chloride, beryllium bromide, beryllium iodide, carbon dioxide, cadmium chloride, mercuric chloride and NO2+. So all these molecules follow the same pattern or the same geometry as here AB2 system. So, to determine the geometry of beryllium chloride molecule, we see the electronic configuration of beryllium where the atomic number of beryllium is 4 and its configuration at the ground state comes out to be 1s2, 2s2 and 2p being empty. And at the excited state, one electron from the 2s orbital jumps to the 2p orbital, and in this way these 2s and 2p orbitals become partially filled. So there is the space for two more electrons that would combine with these orbitals to form the two bond pairs. Here the central atom beryllium retains this configuration and the valence electrons of the beryllium become 2 that are in the second shell where the two electrons reside in 2s and 2p orbitals. So since these 2s and 2p orbitals are in second shell, so these electrons would be termed as valence electrons. Hence the other two ligands that are chlorine atoms here, so the electronic configuration of chlorine having the atomic number 17 comes out to be this one where the valence electrons are in the 3s and 3p orbitals. The total number of valence electrons are 7 here. So every chlorine atom has the tendency to form one bond pair that would be formed with the beryllium over here. Hence, the two bond pairs with chlorine, because every chlorine atom would make a bond pair with the, so one chlorine atom would make the bond pair with 2s orbital and the other chlorine atom would make up the bond pair with 2p orbital. So in this way, these two bond pairs have been drawn at 180 degree like this, and if we see its left structure, then the 7 valence electrons of the chlorine have been shown in the form of dots over here, and the bond pair has been shown with a small line. And in this way, the chlorine-beryllium chlorine bond angle comes out to be 180 degree and its geometry comes out to be linear. So our next system is AB3 system, where, as its name indicates, that a central atom A has been bonded with the 3 ligands that are B. And what does it indicate? That a central atom A has 3 bond pairs with the B atoms. So there are 3 bond pairs of electrons and it has no lone pair of electrons. Hence, if we draw these 3 bond pairs at the maximum distance, then these 3 ligands are placed at the corners of a triangular shape, where the bond angle between BAB comes out to be 120 degrees. Whenever we write down the bond angle, we mention that a ligand, then central atom, and then a ligand like BAB. Bond angle comes out to be 120 degrees, and hence this geometry comes out to be trigonal planar. And examples under this system are boron hydride, boron fluoride, boron chloride, boron bromide, that are in fact the boron halide containing the boron iodide as well. So let's discuss the example in detail, that is boron trifluoride. So in this case, the boron atom that acts as a central atom is attached with 3 fluorine atoms, and to accommodate these 3 fluorine atoms that are in the form of 3 bond pairs, we see the electronic configuration of boron at its ground state. So the boron has 5 atomic number, and the electrons are distributed in the 1s orbital. 2 electrons would be in 1s orbital, then 2s2 and 2p1. So in this way, the valence shell, that is second shell, has the 2 orbitals that contain the valence electrons in this case. So in the valence shell, these 2 orbitals contain the valence electrons with the distribution as 2s2 and 2p1. So this configuration is concerned with the ground state of the boron atom, and at the excited state, its configuration becomes 1s2. Here, 1 electron from this 2s orbital jumps to the 2py orbital, and it comes out to be 2s1, 2px1, 2py1, and 2pz orbitals remains empty. Hence, in this case, these 2s, 2px, and 2py, these 3 orbitals contain the valence electrons that come out to be 3 in total. So these 3 valence electrons make up the bond with 3 fluorine atoms, where the electronic configuration of fluorine is 1s2, 2s2, and 2p5, because its atomic number is 9, and hence the 2p orbitals contain 5 electrons, and still there is a tendency for 1 electron to gain 1 electron in fact. So these 2 and 5, these 7 electrons have been shown in the form of dots here. So 6 electrons are here in the form of duplets, and 1 electron that makes up the bond with the central boron atom has been shown in the form of a short line. And all these three short lines indicate that there are three bond pairs. And this shape is the Lewis structure of the boron trifluoride molecule, and its geometry has been drawn like this in the form of trigonal planar with its bond angle to be 120 degrees. So, its subcategory or the subcategory of the AB3 system is AB2E system, where this A indicates that it acts as a central atom with the two boron atoms being ligands, and here one electron pair or as lone pair of electrons has been indicated with the letter E. This E indicates that there is one lone pair of electrons and two bond pairs that are represented by the B. Hence here number of bond pairs are 2 around the central atom, and the number of lone pairs is only 1. And in the case when there are 3 bond pairs, we place them in a trigonal planar geometry, but according to the postulates of the VSEPR theory, it has been assumed that, or it has been postulated that the lone pair of electrons occupies more space as compared to the bond pair. So, this lone pair would repel these two bond pairs closer to each other and away from this lone pair. Hence, it would occupy more space, so the bond pairs would be contracted, and the value of the bond angle would be contracted, and it comes out to be lesser than 120 degrees. Hence, its shape or geometry comes out to be either bent, angular, or V-shaped. And the examples under this category are SO2, sulfur dioxide, or selenium dichloride. So let's see the examples in detail over here. If we draw the Lewis structure of sulfur dioxide, then the one lone pair of the sulfur has been indicated here, and it forms a double bond with the oxygen, and we have said according to the postulate that the double bond or the multiple bond would occupy more space as compared to the single bond. So the maximum space would be occupied by this lone pair of electrons, then by the double bond, and then the single bond would occupy least space. Hence, if the sulfur would make up the double bond with the oxygen, then these 6 electrons would be shown over here. And in the case sulfur makes up the one or the single bond with the oxygen, then its octet is still completed, because 6 electrons have been shown here and 2 electrons in the form of this bond pair. So total number of valence electrons would be 8. And here still the valence electrons are 8, because 4 in the form of these 2 bonds or this double bond, and 4 electrons in the form of these 2 lone pairs. So in this way, this lone pair of electrons would occupy more space or would repel these 2 bond pairs as far apart as possible from itself, and hence the bond angle between OSO would be contracted and it would become lesser than 120 degrees, and the geometry of this molecule would be bent or just angular. Hence, the selenium dichloride also follows the same structure, where the chloride or the 7 electrons of every chlorine atom have been shown in the form of dots, or 6 electrons have been shown in the form of dots, and 1 electron that makes up the bond pair with the selenium atom has been represented by this short line. And in this way, the Lewis structure has been shown in this figure, and the geometry of the selenium dichloride has been shown over here, where it retains the value of the bond angle lesser than 120 degrees.